talk about another reaction of aldehydes and ketones with uh, amines. Okay, and this is Wolff Kishner reduction. The Wolff Kishner reduction. Oh, that annoying shadow. All right, so earlier in the semester, we were talking about oxidation and about how oxidation uh, usually means the gain in the number of bonds to oxygen. Well, reduction, although maybe in Gen Chem you were told that reduction means a gain of electrons, that doesn't do us too much good here. What does us more good is that a reduction is a gain in the number of bonds to hydrogen. So, did you get that? Oxidation means more bonds to oxygen. Reduction means more bonds to hydrogen. And so we saw in that reductive amination reaction, the nitrogen was getting the carbon atom, carbonyl carbon started out with, just do it over here on the side here, that reductive amination reaction that we just talked about is that this carbon atom here originally has two bonds to oxygen, but then in the product, so this would be like sodium borohydride, pH6, right? You see that this carbon atom goes from two bonds to oxygen to zero bonds to oxygen. It goes from zero bonds to hydrogen to one bond to hydrogen. So that carbon atom got reduced. And this is the hallmark of reduction for many organic reactions, more bonds to hydrogen. Okay, in the Wolff Kishner reduction, what happens is you start out with an aldehyde or a ketone, an aldehyde or a ketone, react that with a special kind of primary amine called hydrazine. Remember we said that a primary amine is NH2, but then that nitrogen is bonded to a third group. Well, the third group that this primary amine nitrogen is bonded to is just another NH2. So we can think of this as a special kind of primary amine. Only in the Wolff Kishner reduction, conditions here are basic. So we would use OH minus, basic conditions, water and heat. And what happens is, first of all, the formation of that imine. So when we were talking about reductive amination a few minutes ago, we wrote down this species where the carbon-oxygen double bond is replaced by a carbon-nitrogen double bond. Okay, and now if we had a reducing agent like sodium borohydride or something like that, we might expect this to become a nitrogen, a carbon-nitrogen single bond with hydrogens added on there, but that's not what happens in this Wolff Kishner reduction. What happens is, I'm going to rewrite this. OH minus comes along. It removes one of the protons from that nitrogen atom, and then swing the electrons this way. Water is produced. And then we have this thing's called a diazine. It's not important what it's called. But we have a carbanionic center here, this nitrogen atom with a negative charge on it, and that picks up a proton from water. Where's this water coming from? Well, it was present in the reaction mixture, and this step just produced it. And so that carbon atom has undergone a reduction, right? See, this carbon atom starts life with 0 bonds to hydrogen. Now it has 1 bond to hydrogen. That carbon got reduced. Okay, last couple of steps here in this mechanism is OH minus comes along, removes this proton, and we shuffle around electrons again. Water is ejected, so is nitrogen. This nitrogen triple bond, and that's a very, very nice leaving group, it turns out. And what we're left with over here is now another carbanion, another dot dot minus on that carbon atom, which then picks up a proton from water, and that brings the reaction mechanism to a close. But we see what has happened here is the complete deoxygenation of the carbonyl group. This carbon-oxygen double bond is gone, and it's been replaced by 2 bonds to 2 different hydrogens. Okay, so Wolff Kishner reduction, it's essentially you're hitting the delete key on the carbonyl group and just nuking that carbonyl group, and now there are 2 hydrogens there. Okay, so that's Wolff Kishner reduction. All right, so I'm going to erase this. I'm going to erase that and just summarize up here. Aldehyde or ketone plus hydrazine plus OH minus water and heat. The organic product that we care about is the deoxygenation product. And then we have a bunch of inorganic junk that we don't care about, which would be nitrogen and nitrogen. Okay, so that's Wolff Kishner reduction. So let's just try some product predictions. Pretty easy, right? All you're doing is you're just nuking the carbonyl group. So what if we started out with this and reacted that with hydrazine, NH2, NH2, KOH, H2O, and heat. So draw the structure of the product. Hope this is going well for you guys. Hope you can see the board and everything. Oh, it's so easy, right? All you have to do is get rid of that carbon-oxygen double bond. Pretend it's not there. And we saw the mechanism for how that happens. So that would be the product there. Okay, so now let's try Wolff Kishner in a synthesis problem. Our target is decane. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Our target is decane, and we want to make this from 2 equivalents of pentanal. 2 equivalents of pentanal, this aldehyde, where now all of the carbons in the target must come from these molecules of pentanal. So whenever we have a synthesis like this, a so-called convergent synthesis, right? What we're going to do is take the first mole of this guy and do stuff to it, and then do different stuff to the second mole, and then hook them all up at the end. Okay, but as always, we're going to try to do this retrosynthetically. All right, so when we're doing retrosynthesis, we're usually looking at the target, and the target has a functional group that we know how to put in. This guy doesn't have any functional groups, right? I don't see carbonyl, I don't see alcohol, I don't see uh, chlorine, nitro group, nothing. But that is significant because the Wolff Kishner reduction is a way of getting rid of the carbonyl group. So this molecule could be made from an aldehyde or a ketone, which was then subjected to Wolff Kishner conditions, and then those conditions nuked the aldehyde or ketone. Okay, the only thing is where to put that aldehyde or ketone. So two equivalents of that. So I'm just going to rewrite it. So these are the two equivalents that we're dealing with. How about dot, 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 dot? They're the first five. And then star, 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 star. They're the second five. Where are they in the target? And the reason I'm going through this is because this is going to give us some insight as to where to put the carbonyl group. Dot, 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 dot. Stop. Those are the first five. That's from here. And this is the second five. That's from here. And so the critical step in this synthesis would be creation of this bond here. And so even though I could put the carbonyl here and get rid of it with Wolff Kishner, even I could put the carbonyl here and get rid of it by Wolff Kishner, or here, or here, or here, or here. It really makes the most sense to put the carbonyl here where the stars and the dots hook up. Okay, so I'm going to do that. That's going to be easiest. So I'm going to use this reaction, this Wolff Kishner reduction, that gets rid of the carbonyl group. And I've decided that the most logical place to put the carbonyl is going to be there so that it mimics and looks like our target. I mean, our starting materials. So if I could only make this, I could just subject it to Wolff Kishner and get rid of that carbonyl group and come up to this. Okay, so now I want to see how do I make this. This becomes our new target. It's a ketone. We have lots of ways of making a ketone. But the most logical one that's going to allow us to use these two 5-carbon units is going to be what? How are we going to make this ketone in a way that's going to allow us to use these 5-carbon units pretty much as is? Are you thinking about that? What reaction are you going to use to make this ketone? Well, we know that a ketone is the product of the oxidation of an alcohol. So our real goal is how to make this alcohol using these 5-carbon subunits pretty much as is. And so how would we make this best way? Grignard reaction. Okay, so we would use this aldehyde. So that is this. So we've used him, check. Reacting with something like a Grignard reagent. Now this is going to be the other 5 carbons. 1, 2, 3, 4, 5. This plus this, then H3O plus. And so that's how we could make that, alcohol in a way that preserves these 5-carbon fragments. Okay, so now this becomes our new target, and doing this retrosynthetically, how do you put MgCl on stuff? You add magnesium to the corresponding halide. So you would need that 1-chloropentane in order to make this Grignard reagent. And how do you put Cl on stuff? Orgo 2 style, right? That would be with that Darzens reaction, thionyl chloride and pyridine. But that's a reaction of an alcohol. primary or secondary alcohol. And I know a reaction where I can make this alcohol from my second equivalent of aldehyde, right? Because my whole plan here is to use this guy and use this guy, do stuff to one of those moles and then do different stuff to the other mole. So how are we going to go from this aldehyde to this alcohol? So I guess the important critical thing to notice here is that this carbon is bonded to one hydrogen. This very same carbon is going to be bonded to two hydrogens in the target that we're looking for. It's an increase in the number of bonds to hydrogen, and that is a reduction. So the most common mistake that people would make here would be you go from an aldehyde to an alcohol using PCC or Jones. That's oxidation. Jones, PCC, all of those, that's a way of going from an alcohol to an aldehyde or ketone. But here we're going from an aldehyde or ketone, in this case an aldehyde, to an alcohol. That's a reduction. This carbon is gaining more hydrogen. So what would be the reagent that we would use to reduce an aldehyde to an alcohol? Thinking about that, how do we convert an aldehyde to an alcohol? We know how to make an alcohol from an aldehyde. That's Jones, that's PCC, that's all that other stuff. Well, it wouldn't be Jones because I would take it to a carboxylic acid. But that's PCC, DMP, Swern, all that other stuff. That's aldehyde to, alcohol to aldehyde. But from aldehyde to alcohol, that's reduction. And so here we would have a lot of options here. We could use sodium borohydride, or we could use lithium aluminum hydride, or we could use hydrogen and some kind of catalyst. Okay, those are the reduction reactions. And so there's our synthesis of decane.